Okay, so, well, do you have any questions before we start? Any questions?
On the last page, the point set by F1, we say that F1 does work when it rotates. And what if it rotates to its original point?
Now, we will study the work done by such a force in more detail in a moment. Any other questions? Okay, so let's study this torque due to the weight of an object. Let's just assume we have this rigid object rotating around this point. It's free to rotate around this axis. Now the torque due to any force would have been the point at which the force is acting cross the force itself. Now let's see, the weight is acting at every point. So if you just imagine there is a point over here, it has a weight. This point, it has a weight. This point has a weight. This point has a weight. So the torque would be nothing but the position of that point cross product with the weight of that point. Now the weight of an object, weight of that very small point is nothing but mi times g, the weight force. Now this we can just write as mi times ri cross g. But you see, g is a constant vector. Now constant we can always take it out of the summation sign. So this is equal to mi times ri cross g. What is this vector? This vector over here. mi ri, this is equal to? Remember, I is mi times ri squared. Furthermore, I is just a number. It's not a vector. You see here, I'm multiplying vectors with numbers, which is a vector, and summing all these vectors. So this whole sum is a vector. It cannot be I. This is, if it was divided by the total mass, then it would have been the center of mass. So this is nothing but m times the center of mass. You see, first of all, this cannot be I. At least one reason, I is just a number. Here, this is a vector. Now, if you remember the definition of the center of mass, this is how we had defined the center of mass position. You just take the masses, multiply by their position, sum all over them, divide by the total mass. This is the average position of all the masses, which is how we define the center of mass. So this sum over here is nothing but m times our center of mass, which we can also write as r, the position of the center of mass, cross w is m times g. It is the weight of my object, the force due to the weight of my object. Now, before we had seen one property of the center of mass. We could treat the object, if we have an expanded object, its translational motion, we can just describe its translational motion as if it was a point mass right at the position of the center of mass. So we could use all the Newton's law, Newton's second law, and if the total force was given, then the acceleration of this point is determined by the force divided by the total mass, etc. Now we see another property of this center of mass. So the weight of an object, assuming that g is constant, the weight of an object is a force, and if we want to calculate the torque due to the weight of an object, we can just assume that the weight is acting only at the center of mass. This is our proof. The weight actually, it just acts everywhere on our mass, but the total torque created by the weight acting on every part is equal to as if all of the weight was acting on the center of mass of my object. So if I want to calculate the torque due to the center of mass, this would just give me the torque. Any questions on this one? Let's do an example. Suppose we have this wall and there is a rod attached to it. It has a length L, total mass M, and it is uniform. And it is free to rotate around this point. So you can just imagine you have this rod, you just allow it to rotate from this end. This end is not allowed to go away, but it can rotate around that axis. It is fixed. So the moment that I release this hand, or at this instant that we just leave this rod free to rotate around that axis, what will be its acceleration? What is the acceleration of the center of mass? Let's say the torque, the moment of inertia is I. What will be the acceleration of the center of mass? So will it be 0? So if the acceleration of the center of mass is 0, that since initially it is not moving, the center of mass, the acceleration is 0, so its velocity will not change. Its initial velocity will be 0, so its position will not change, so it will always stay there. But we know that if it is free to rotate from this point, it will rotate. The acceleration. Well, of course, at every point, as the object is rotating, they will have a central acceleration and also a tangential acceleration. The central acceleration is always the speed squared divided by the distance from the center. At this instant, the speed of the center of mass is 0. So there is no central acceleration at this instant. There's only... What are the forces acting on my system, by the way? Your friend is saying that there is weight. Okay, we had just shown that weight acts as if it is acting right at the center of mass. So this is the position of the center of mass. So this will be the force due to the weight. Now, are there any other forces? This point, okay, so your friend is saying that there is also the force acting over here. So our hand is holding it there, so our hand should exert a force. But it's free to rotate, so does it still exert a force? It is free to rotate. How much force will it exert? Do we know? Or if it will exert some force, how much will it exert?
It will exert some force because the center of mass accelerates towards...
Well, at this instant, no. At this instant, what is the acceleration? At this instant, what is the force that this point exerts, if it exerts any?
0.
So you are saying that there is 0 force that this point will exert. Well, let's see. Let's calculate this study. Now, we already have one unknown, this point. The force is acting over here. Now, one nice thing about the torque is that it depends on the position vector. So furthermore, you see, this is torque is R cross F. This is the torque of an arbitrary point. my object is rotating around this point. So let's calculate the torque acting on that point. I don't know what force is acting over here. Let's just call it F. It might be 0, it might not be 0. It might be in the vertical, horizontal, etc. We don't know yet. So, but nevertheless, let's calculate the torque for rotations around this point. There will be the torque due to the force F. This force, what is the torque? Created by this force relative to this point. 0. Basically, although we don't know what F is, R is 0 for that point. This is the rotation axis. This force is acting right at the rotation axis. So this will be 0. And the torque due to the weight L over 2, because it's this is our center of mass. Torque due to the weight is our center of mass cross the weight. This is equal to, well, the magnitude at least is the product of the magnitudes L over 2. Weight is m times g. Sine of the angle between the two, sine of 90 is just 1. So what is the direction? Let's say Z is out of the screen. Minus Z. So let's see. Okay, this is R, this is W. Let's just imagine R is rotating towards W. Take your right hand, throw your fingers in the direction of rotation. So this is into the screen. It is in the minus Z direction. This is the torque. The acceleration, angular acceleration, it's just torque divided by I. This is mgl divided by 2I in the minus Z direction. This is alpha. Now we already know one thing. The tangential acceleration is equal to R cross alpha. No, omega cross alpha cross R. Now we want to find the angular acceleration of the center of mass. So it should be alpha times our center of mass. Now we can write the magnitude, which is the product of the magnitudes mgl over 2I. Our center of mass, it has a magnitude L over 2. The angle between the two vectors, this is the vector alpha. And this is the vector alpha. This is the vector r. The angle between the two is still 90 degrees. Sine of 90 is 1. And what is the direction of alpha cross r? Well, here I made a mistake probably. It's r cross alpha. No, alpha cross r. Okay, this is alpha, this is r. Now alpha cross r is pointing downward. Let's say it is the x direction, so it is in the x direction. A tangential of the center of mass is equal to mg L squared over 4I in the x direction. Now for this rigid roll, I should be m L squared over 3. So the tangential acceleration of the center of mass, which is in fact nothing but the acceleration of the center of mass because it doesn't have any radial acceleration yet. At this instant, it is at rest, so the central acceleration is just 0 at this instant. So this will be equal to mg L squared over 4 times 3 over ml squared in the x-hat direction. Okay, ml squared, they just cancel. This is 3 over 4g in the x direction. So the acceleration of the center of mass is less than what would have been if it was not fixed at this point. So basically, this point, the point that I'm holding, I should be exerting some force on that point so that that point doesn't move. Otherwise, without that force, both points just accelerate downward with the same acceleration, so my object doesn't rotate. Since this point is fixed, although it's allowed to rotate, there is a force that I'm exerting at the tip, which causes the acceleration of the center of mass to be lowered by what would have been if it was not fixed over here. Now, what is the force? What is F? Now we can calculate the force F. What is the total force acting on my object? The total force acting on my object is nothing but this force, this unknown force F, plus the weight of the object, which is F plus m times g in the x direction. This x direction is downward in the direction of the weight. And we had already seen the acceleration of the center of mass. The total force acting on my system should also be equal to m times the acceleration of the center of mass, which is mg 3 over 4 in the x direction. So this, on one hand, this is the total force acting on my system. There is this unknown force F. On the other hand, we had already calculated the acceleration of the center of mass of my system. And the total force should be nothing but the mass times the acceleration of the center of mass. So this tells me that F is nothing but minus mg over 4 in the x direction. So it is straight up, and the magnitude of that force is 1/4 the weight of the object. Now, any questions up to this point? Now, if you see, let's start from the beginning. This was our example. We have this rod that is free to rotate. Since there is already an unknown force, this F we don't know, so we cannot really directly use Newton's second law. We cannot just say the total force acting on this is mass times the acceleration, because basically we don't know the total force without first calculating this F. But we already know something, that we can treat it as a rigid body. It is rotating around this point, and since it is rotating around that point, this unknown force F does not contribute to the torque. The torque created by this force F for rotations around that point is 0. So the torque of that point is 0. We already know the weight. We can calculate the torque created by the weight. And from that torque, we can obtain the angular accelerations for rotations around that axis. So we already know the angular acceleration. But if we know the angular acceleration of any rigid object, we can calculate the tangential acceleration for any point on my object, including my center of mass. Since I know the angular acceleration, I can calculate the tangential acceleration of every point. So if I calculate the tangential acceleration of the center of mass, using the angular acceleration, this is what I obtain. This is the tangential acceleration of the center of mass, and since initially the center of mass has 0 velocity, it won't have any central acceleration. The only acceleration that the center of mass is the tangential acceleration, which is pointing downward. And since it's pointing downward, this is the acceleration. We already know since we know the acceleration, we can calculate what should be the total force acting on the object now. We already determined the acceleration. This should be the total force. The total force has two parts. There is this unknown force F. There is plus the weight of the object. So this is the unknown force F. It is pointing upward, and its magnitude is 1/4 the weight of the object. Well, let's say that I wanted to avoid all the boredom of calculating I in the class, but if you like, you can have it as a homework. I mean, I have calculated I so many times I already know what I is. If you want, we can calculate I. Now, I will leave it as a homework. Well, let's do it. I mean, at least one example. This is our example. We have this rigid rod. We want to calculate the moment of inertia of this rigid rod. And let's say that rho is mass per unit length. So basically, rho is m over L. Now we know the definition of the moment of inertia. MI/RI squared. Of course, this is true if we are talking about point objects. This is a continuous mass, but I can divide it into very small parts. These are my very small parts. I can just take one of them. Let's say that is at a distance x from the center, and it is with, let's just call it dx. So the moment of inertia will be nothing but, the mass of that part is nothing but m over L times dx. This is the mass per unit length. My segment over there has length dx. So this is the mass of my segment. And it is at a distance x from the center, from the axis of rotation. This is my moment of inertia. Now I have to calculate this sum. But of course we will be taking the limit when each one of these segments is infinitesimally small. I have infinitely many of them. So that is nothing but my integral. M over L x squared dx. X starts from 0 up to the total length. Changes from 0 to L. So this is m over L x cubed over 3. X is equal to from 0 up to L. This is m L squared over 3. This is the moment of inertia of a rigid rod for rotations around its end. This is not for arbitrary rotations, but if you have this rigid rod and if you are rotating from one of its ends, this is the moment of inertia of it. So this is what you are saying. This object is rotating like this, and you also let it rotate in this sense. Now, those kind of rotations you will study in your third year. Now, this year we will restrict ourselves to rotations in which, well, up to now we always studied rotations around an axis that are fixed. In the next hour, probably we will start for studying rotations around an axis that is not necessarily fixed, but its orientation is constant. For example, we will look at this example. Now, this is an example I like. You take the ball, you just rotate it. So the rotation axis is, it's rotating around this axis, and you just release it on the ground. Again, it will start moving. Its rotation axis will still be all the time this axis. But we will not look at cases in which the rotation axis is also changing its orientation. Or let me put it this way. You get bored about calculus. Okay, so that will require a bit more mathematics. F will change over time. This is the force F necessary to keep it when its orientation is like this. You see, if the object, when the center of mass is over here, you see the center of mass at this instant, it has both the tangential acceleration and the central one. You see, the weight causes an acceleration in this direction only. So the acceleration vector is some pointing in this direction. So the force acting at this point will have a component in that direction also to create the total acceleration. Other questions? Well, let's look at the work done on a rigid object. This is our rotation axis. We will assume it to be fixed. This is our rigid object. There can be all kinds of forces acting on it. Let's say this is at this point Ri. There will be a force Fi, and here we have another force F prime, etc. F double prime. There are all kinds of forces acting at different points. And of course the system will be creating some torque. Now the work done on the object will be nothing but assuming a very small amount of work. To calculate the total work done, we can just sum all these small amounts of work. Now the work done by a very small displacement will be nothing but Fi dot delta Ri. Now this delta Ri is the displacement of the point that the object, that the force is exerted. So I have this rigid object. I exert a force over there, here, let's say in this direction. So this point is displaced by this much. Now let's look at this point. Let me draw a clearer picture. This is my rigid object. Initially, there is initially a force over here. Let's say it's constant. At the next instant, it would rotate slightly. That point is now somewhere over here. So this is the displacement vector of that point. Let's say this angle here is delta theta. This angle, now let me call that this angle theta. Now, what is the work done by this force? This is 90 degrees. What is the very small amount of work done by this force Fi? You see, the displacement is delta Ri. Well, we know that this is already Fi scalar product with delta Ri, which is nothing but Fi, the magnitude, times the magnitude of delta Ri, times the cosine of the angle between the two. Now, what is the angle between the two? Well, you see, this angle is theta. I need this angle over here. Now, hold on. That angle, delta theta, is all of this angle. This angle is theta. So this angle over here is theta minus pi over 2. Because this delta r is perpendicular to this vector for very small rotations. I'm considering a very small amount of rotation. So this delta r is perpendicular to this vector. So this whole angle is by theta. So what is left between the r displacement vector and the force F is theta minus pi over 2. So here I have the cosine theta. This is delta Ri times cosine, let's say this is theta prime. Now this here over is the angle between F and delta R. It is this angle over here. Theta is the angle between this line and the force F. So I'm using a different symbol, theta prime. What is cosine theta minus pi over 2? Sine theta. Does this ring any bells? Well, this is the magnitude of the cross product. This is the magnitude of F cross delta Ri, Fi cross delta Ri. Now, delta Ri will be constantly changing. Let's relate everything to something else that might be constant. Let's say that by the way, okay. Now, what is delta Ri, the magnitude? Let's call this angle delta phi. This is Ri times delta phi. Do you agree? We are, okay, so let's repeat it. I have this rigid object. I'm exerting a force over here in some direction. Let's say at this example, this is the point that I'm exerting the force, I'm pushing it downward. So this point is displaced from here to here. So this is the delta R. This is the displacement of this point under the influence of this force F. So I have this force F, which causes a displacement delta Ri. So the work done by this force F during this rotation, by the way, there might be other forces acting on my system. But the important thing is that even if there are other forces acting on my system, the object is rotating. This rotation need not be caused by this force F. The important thing is that my system is rotating. So this point is being displaced, and the point at which the force is acting is also being displaced. So there's a work done by that force, and the work done we had always defined it as the force times the displacement, F times delta R. So this is the work done. Now, of course, now I have to calculate that scalar product. Now, in this example, I defined several angles. One is, okay, this is the position of my object, of the point at which the force is being exerted. The force, let's say, is pointing in this direction. So there is an angle between this position vector and the force, which I call this theta. Theta is the direction between the position vector at which the point is acting and the force itself. Now that point is being displaced by delta Ri. To calculate the work, I need to calculate the angle between my force. Well, in this example, this is the direction of the displacement vector. This is the direction of the force. The work is defined as the magnitude of the force, magnitude of the displacement vector, times cosine of the angle between the two. Now, the displacement vector and the position vector, they are always in 90 degrees. This point is just doing circular motion. Not necessarily uniform, but circular motion. And in circular motion, very small displacements are always perpendicular to the position vector of the object. So this delta Ri is perpendicular to Ri, which tells me that this angle between delta Ri and the force F, you see, this angle is theta. This angle from here to here is 90 degrees, so what remains is theta minus pi over 90 degrees. And cosine of theta minus pi over 2 is just sine of theta. Now, any questions up to this point? Now, delta Ri will be constantly changing depending on the force. Or at the point, for different forces, delta Ri will be different. I want to relate it to something that is the same for all the objects. So let's look at here. The delta Ri, the delta W is, this delta Ri I can always write as Ri times delta F. Because initially this was my position vector. Finally this is my position vector. For very small changes, this length is nothing but the length of the arc. And the length of the arc is, this is how I define the length of the arc. This delta phi is how much my rigid body rotates. So the work done by this very small object as it's rotating will be the magnitude of the force Fi. Now delta Ri is Ri. Delta phi times sine of theta. Let us calculate the power. The power will be nothing but the work done per unit time. And this is Fi times Ri times sine of theta times delta phi over delta t. You see, now the power is Fi times Ri times sine theta is nothing but the magnitude of the torque. And then I have delta phi over delta t is nothing but the angular velocity of my object. Now the total power will be nothing but the sum of the powers of each one of the forces. This is equal to sum of Ti omega this is the total torque times the angular velocity. Now let's go back to this example. What is the direction of the torque? In this example, what is the direction of the torque? Let's assume that there are no other forces acting on my system. My system is rotating like this. What is the direction of torque? Torque is R cross F. Just imagine R is rotating towards F. So it is into the screen. Torque is into the screen. Well, what is the angular velocity, the direction of the angular velocity? Remember, delta phi is rotating from here to here. It's also in the same direction. So the torque and the angular velocity are in the same direction. So this is their scalar product. So the power of all the forces acting on a rigid body is determined by the torque acting on the system, not by the total force. Of course, again, here I'm repeating that we are only looking at cases where the system the axis of rotation is at rest. So if the axis of rotation is at rest, then the total power of the forces acting on my system is given by the torque times the angular velocity. Or if you want to calculate the work, you can also write that the work will be the torque scalar product with the, let's say, angular displacement around that axis. Again, if you compare it with F is equal to F dot delta x, now the torque again plays the role of the force also in the work. Okay, any questions on this one? Now here, this was just the application of the concept of the work and the torque we already knew before. And the work kinetic energy relation will still hold over here. The work done will be equal to the change in the kinetic energy. This time it will be the rotational kinetic energy around this fixed axis. Any questions? Now let's do an example. We have our rigid body, which is our wheel. Now in this case, I will assume that the fork is always tangent. It is a constant force, but since it's a tangent, the torque will be constant. Let's say this is the z-axis. The total torque acting on my system, let's say it is T0 in the z direction. What is the power? Now what I will be doing is, I'm exerting this force. It will start rotating. What is the direction of the angular velocity? It is pointing downward in the direction of the torque. So the work at a given instant will be, let's say, omega z. Of course, since there is a torque, there will be an angular acceleration. So the angular velocity will be a function of time. Now the power will be that the total torque, and this is equal to omega t times tau. Now the torque we can also write as omega t times I d omega t by dt. This is the angular acceleration. Power is nothing but the work done on the system in a given amount of time. Okay, one bad notation. This is W. The other one, this is omega. It looks like W, but it's slightly different. So this is not W, this is the angular velocity, this is the work done. The work done per unit time is what we call the angular velocity. the work done per unit time is what we call the power. So what we can do over here is we start from some initial time. In the initial time, let's say the angular velocity was 0. So there is no work. Initial time, there is no work done. Finally, this is the total amount of work done. In this time, during this interval, initially omega is 0. Finally, it is some final value of omega. This will be omega is equal to 1 over 2I omega squared. Omega from 0 to omega. This is the total work done. Now this is basically a proof of the energy-work relationship. Now, okay, let me do the last step once more. Okay, this is what we had obtained. This is per unit time. Or we can also write this as dW is equal to omega I dW. So the work done, a very small amount of work done on the system is related to a very small change in the angular velocity of my system. Now to calculate the total work done, I have to sum all the small amounts of work that I have done. The W, initially I haven't done any work, so finally the total work I have done is omega total. This should be equal to I omega dW. Initially angular velocity is 0, finally angular velocity is, let's call it omega f, or we can even say initially it is omega I, angular velocity, finally it is omega f. So omega total is just equal to 1 over 2 I omega squared. Omega changes from omega I to omega f. This is 1 over 2 I omega f squared minus 1 over 2 I omega e squared. This is the total work done on my system. Well, on the other hand, omega total, 0 to omega tot of dW, 0 to dW, we also know that it is omega times tau 0, omega times tau 0 times dt, because we know that power is omega times tau 0, power is dW by dt. So dW is omega tau 0 dt. So the total work is omega tau 0 dt from initial time to the final time. Well, remember, omega changes with time, but omega is the change in the angular position of my object. So this is just like velocity integrated over time. Velocity integrated over time gives me the total displacement. Angular velocity times the time integrated over a given time gives me the change in the angle. Yes.
My question is thinking about 3 slides before. You said
This one.
no. change now is an arc.
Now, the change in a vector is never an arc.
For change now, that particular rigid body moves to an arc, that point at the rigid body moves to an arc when it rotates that.
Okay, you see, the displacement, the change in a vector is always defined as the final vector minus the initial vector. This is always the definition. I don't care what it does in between. The change is always the final value minus the initial value. Whether it moves like this or it moves like all the kind of fancy movement and comes here, it has no effect whatsoever in the displacement.
Because for normal displacement, it's a linear displacement. This is an angular breakdown.
No, this is a linear displacement. I'm not looking at any angles. This is the definition of the work.
But that point doesn't move linearly.
I don't care.
So my question is, why should you use the linear displacement of
I don't care. I'm not assuming it's making a linear displacement. The only thing I'm saying is the work done by a constant force is always equal to the force times the displacement vector. By the displacement vector, what I mean is the final point minus the initial point. I don't care what kind of motion it does. So at this step, whether the object is following an arc or going along a straight line or making any kind of fancy motion, I don't care. This equality always holds. But going from this step to this step, this also holds. This is just a definition of the scalar product. The only place where I use that it is going around an arc is over here. Since it is going all around, even this one doesn't really use that it is going around over an arc. It just assumes that these 2 points, they're equidistant from this center, and the angle between these 2 points, the initial and the final point, is very small, so that this length over here is almost the length of the arc. This is the only place somehow I use the fact that it's going around an arc. I don't care what kind of motion it does. It doesn't make any difference. Of course, since this is a rigid body, it is going over an arc, but that fact doesn't change any of these derivations.
Yeah, because, for example, if you have, let's take, I assume, because you are looking at a point mass on that.
No, I'm not looking at, I'm just studying one force. I'm not studying a point mass. This is my rigid object. This force is acting, let's say, at this point, and that point is being displaced. So I'm calculating the work done by that force.
But there is no way, if you displace that point with that force, there's no way to move linearly. That point.
You see, I don't care whether it's moving linearly or not. Well, as I said, whether it is moving around an arc or whether it is doing any kind of other fancy motion, the work done by a force as an object moves from the initial point to the final point, if the force is constant, the work done by that force is always equal to the force scalar product with the displacement vector. It is this vector. What that point does in between, whether it's moving along a straight line or this arc, it doesn't change this fact.
Well, I'm not really satisfied about here.
Other questions? Okay, let's give a 10-minute coffee break.